Hey, Csauce, Drason here, and how big is the world's biggest magnet? Is it 100 meters across? 1,000 meters across? 1,000 kilometers across? Well, actually, by diameter, the world's largest magnet is 1.274 million kilometers. The Earth is the world's largest magnet. But don't get too attached now, since at its surface, the magnetic field is only a mere 45 microteslas. It's enough to attract the needle of a compass, but not much else. I was reminded of this when I was looking through our new Wonderment Cube. For those of you who don't know what that is, it's a weekly subscription where you get cool stuff from me and the guys. Thanks! Let's take a look inside, shall we? Hey look! A couple handy-dandy magnets. But wait, what are these? In order to discuss magnets, we must first discuss magnet type. The first civilization to discover the properties of magnetite was ancient Greece. As the story goes, a shepherd was walking through the field one day when he noticed the nails on his shoes sticking to a mysterious rock. This rock was magnetite. Meanwhile, in nearby Rome, the great philosopher Pliny the Elder had discovered magic. Well, not exactly magic, but magnetism. He had discovered that a hill in ancient Rome was strangely attracting various objects, mostly metal. But the hill was magnetite. The ancient Chinese would later prove him wrong. There's been evidence to suggest that the ancient Chinese, as early as the Han Dynasty, have been using the magnetic properties of magnetite for certain divination ceremonies. They would place a magnetite spoon on a bronze plate and let it spin. The direction the spoon landed on would indicate the orientation of good and bad luck in the environment. And while we began to use magnets as tools, we really didn't begin to understand them until around the early 1800s. That's when Hans Christian Ørsted made a discovery that would change everything. It was one day in July 1820. He had placed out a copper wire and a power source as a demonstration to his students about how electric current flows through a wire. He also happened to have accidentally left out a compass. So Hans Christian Ørsted went on and connected the wire to the power source. What he found was that the compass would be affected as soon as he touched the wires to the power source. So what was going on there? Well, Hans Christian Ørsted concluded that the wires were creating a magnetic field due to the electric current. Hans Christian Ørsted's experiment was pretty cool. It's also a thing you can do at home now, guys. All you have here are a few common household items and a copper wire that we got from a hardware store. This is also a compass. You'll need that to see the effect of your Ørsted experiment. So while Ørsted didn't actually use an iron core, we can actually use this iron core and coil our copper wire around it to get an enhanced effect. So what we're going to do is coil our wire around like so.
Now once you're done, just kind of like...
Alright. And now all we have to do is connect both ends to the positive and negative ends of the battery. Look at that. But wait, how does this work? It's almost as if the electricity flowing through this wire is awakening some sort of magnetic essence in this iron core. Well, we obviously know that's not the case. Well, actually, it is. But it would take another 100 years before someone would figure this out. You might have heard of him. His name was Albert Einstein. In 1905, Einstein published a paper on his theory of special relativity. Special relativity states that moving objects experience time differently than non-moving objects. But what does this have to do with magnets? Or more specifically, our magnet? Well, for a moving object, special relativity states that space around it appears to compress. So, objects moving along with the electrons in the wire tend to see the protons in the wire fit closer and closer and closer together. When the protons fit this closely, it creates a net positive charge in the wire. The electrons are moving relative to you, so they appear more spread out. This makes the positive charge intensify even more. To see why this is relevant to magnets, we first need to consider the current we just generated in the wire. A current is just moving electrons. So if I started moving in the direction of the current, I'd see the electrons moving slower and slower. And because of relativity, the electrons would appear more spread out. Then for the non-moving positive charges, I'd see them moving faster and faster as I move away from them. These positive charges would contract due to relativity as they're moving faster than I am. This creates a higher density of positive than negative in the wire, creating a positive charge in the wire. Miniphysics actually did a great video on this, and you should totally check them out. So magnetic forces are really just electric forces from a different perspective. And as Maxwell's shown, electric forces can be generated through a changing magnetic field. So electric forces are really just magnetic forces from a different perspective as well. But no. Electric forces are not just magnetic forces from a different perspective. For that to be true, there would need to be magnetic current. And for magnetic current to be true, there would need to be magnetic monopoles. But then, what are magnetic monopoles? It just seems strange that, while electricity has isolated charges, magnetism just doesn't. Ultimately, many scientists felt the same way, and even before Maxwell's equations, they've been looking for the elusive magnetic monopole. But all have failed, except for monopole enthusiast and scientist Blas Calabra. Blas Calabra would eventually go on to build a detector using 8 magnetrons. This detector would register different signals for different magnetic particles flying through the detector.
3, 2, 1.
Blas Calabra would eventually build a detector using 8 magnetrons. This detector would register different number of signals for different types of magnetically charged particles flying through the detector. If a monopole were to fly through the detector, it would register a solid +8 and then 0. The experiment would go on to sit there for quite some time, and Blas Calabra would eventually lose interest. But on one fateful Valentine's Day, 12 years later, a signal would appear in the machine saying +8. Needless to say, the entire physics community went ecstatic. Physicist Steven Weinberg even wrote a poem for the occasion. Roses are red, violets are blue. It's time for monopole number 2. And so, physicists would go on to build bigger and better detectors than ever before in hopes of detecting that second monopole. But it was never found. To this day, that monopole reading is seen as a rare anomaly, a glitch in the system. If we were to ever discover a true monopole, everything we would know about physics would be wrong, and everything we would know about electromagnetism would have to change. But magnets as we know them today have 2 poles. In a sense, magnets and people are very similar. When people are apart from society, they experience something called loneliness. People are meant to be social. They're not meant to be monopoles. So go out, take inspiration from magnets, find a partner, and as always,